Okay, so let's start. So today I have a bunch of content. So if you upload it, you will see two LDA notebooks and one on movie recommendation. Um, so I kind of realized last time that there's a lot of assumptions I made about your probability and stats and math background, but uh, I made some assumptions that were not true. I could sort of go into, literally at least 50 minutes on the blackboard explaining to you what an EM algorithm is with a simple example, but maybe we'll do that. I have some notes here. But what I would like you to maybe do instead is to understand what I did to learn these things in like an hour. Right? I kind of know this from before, but I forgot, right? It's been a while. So what textbook I used, what pages I read. And so the idea is that you can do this to not just this particular standard algorithm, but others as well, right? So what did I do? So why do we need EM? We need EM because it's a very standard algorithm you will use in various probabilistic machine learning models, especially those that have a generative or Bayesian scheme. So I do also want to mainly walk through this so you have all the bells and whistles of how to run the LDA on this particular data set, so that the other guys who are not here, who are trying to do a project on using k-mers of contigs from genomes to identify the K species, for example, they can essentially adapt this quite quickly for their context. Okay, so I basically looked in the index for EM algorithm, and this I said is one of the recommended readings, Elements of Statistical Learning by Trevor Hasty, Robert Tibshirani, and Jerome Friedman. So there is page 236, section 8.5. There's a section on expectation maximization algorithm or EM algorithm. And I will try to find a PDF of these few pages. So basically from page 236 to 240, they basically give you a very simple example of a mixture of two Gaussians, two normals with unknown parameters mu1, sigma 1, and mu2, sigma 2. Okay, so you have observations from this mixture of two Gaussians, and your objective is to estimate not just mu1, mu2, sigma 1, sigma 2, but also the weight, the mixing weight, say pi, probability pi. The sample is from the first component, the first Gaussian, and 1 minus pi is from the second one, right? So that's the simplest example of a latent variable model or a hidden variable, where the hidden variable is you don't know which component of the two mixtures your data is coming from, because it just comes at you as a number. You don't know whether it's coming from the first distribution or the second. Then what you do in these classes of models is you augment the space, the parameter space, or whatever you want to call it. You augment it to have, in this case, two binary outcomes: 0 if it comes from the first component, and 1 if it comes from the second. Right? So now this is called the augmented space, and in this augmented space, you have to now define the likelihood, and I'll start crawling there. And there's one thing called the E step and M step. So instead of getting into the details of this, I'm going to try to hunt down this PDF for you guys quickly. So maybe what I'll do, maybe in the future, is volunteer someone to do a presentation on the Blackboard. Okay, it'll be good for everyone, right? Or I can do this too. So let's do this. All right, so let's sort of slightly black box a few things. So in the end, what is the EM algorithm doing in these sort of latent variable models? It has this augmented framework, and it has two steps that essentially allows it to maximize the log likelihood function. And so you can fit parameters, okay? So So let's just jump in here. Okay. So we were already looking at this last week, right? So we had various things we were doing. So this is the 20 news group dataset. And so you guys, so we did this the hard way, right? I will show you in the end, there's like a little homework for the easy way. But the hard way is basically downloading the dataset, putting it into your own directory. So has everyone done this step on their community edition? Because this is like a 10-minute loading time, right? So now you have each news group's 100 articles inside each of these directories, right? So in fact, you know, what we could do is take these directory names as the actual topics, right? This example is great because you know exactly what the 20 news groups are, the 20 topics are. So so if you were to do this as a supervised clustering problem, then you can use the actual information on which news group each one comes from. But we are of course going to pretend that we don't know, and then because we are interested in using KMeans in the standard setting, which is the unsupervised setting, where you do not know. And the second notebook, where we analyze the Cornell movie dialogues, we really do not know how many types of dialogue are there, right, across some English Hollywood movies. Okay, so we'll pretend to be an unsupervised setting here. And the only point to remember is if you recall the actual Databricks data set on the same 20 news groups, they actually already classified into the labels. They know which of the 20 news groups it belongs to, so they can sort of see how well their unsupervised method is doing. Okay, so that's something we can do later on. So we first did this. We did this whole text files thing, which gives us the file name and the content. And then we realized there is 20 groups and 100 files per each. So that's 2,000 elements in the corpus. And we took 5, and then we realized there is this double line break, which I can use as a way to split my files. Okay, so it's sort of okay. And if you really look at it, it's not ideal because there are all sorts of other things. There is that we are picking up. But later on, we are sort of doing a filtering, which I'll point out later, where we only keep words that appear in at least X number of journals, X number of documents, right? Each of these 2,000 documents. So we can do a lot of filtering kind of easily using those hyperparameters for the method. But of course, the right way to do this would be to really get inside and do a bit more parsing. Okay, so here's just taking random samples, and this is how I sort of said, okay, there's this 2 end-of-line character, and I'll just take all the text content below it, right? So it's not too bad. Okay, so then that's what this is doing, corpus body, and simply split it, dropping the top part and making strings with white spaces between them, and then just making sure I still have 2,000 things in my corpus body. And just simply checking things again. Yes, it's been shaved off. Right. Yeah, looks okay. You see there are all these email addresses and things like this, but they will sort of not play a big role down the road. But the right way to do it would be to get rid of them as well. Okay, so of course we said we wanted to use these feature extraction and transformation APIs. One thing I just remembered is if you start scaling this up like crazy, like maybe Mariama and Lee's project, say you want to apply K-means after you do this hashing, instead of using the standard K-means, there is another K-means, which actually comes up with this, which uses this more clever locality-sensitive hashing method. It's called K-means LSH somewhere. It's in the ML-lib or ML library. Okay, so yeah, so make sure you look here because you don't want to roll your own. Okay, so we were doing all these things yesterday or last time. So now I'm simply doing a zip with index and associating an ID with each document in my corpus because that is needed downstairs. And then step 3 was text tokenization. So we said we can do a more general regex pattern. So for example, you could, this is a good homework. You could expand this and try to remove emails and other patterns, right? So you could do this. That's good. But anyway, because we just took the stuff and broke it on white space, we're just using this white space pattern. But see, now what I'm doing is setting minimum token length of 4. This will simply filter away any token, basically words here, with length less than 4. So that gets sort of little words, which may or may not be good, unless say your corpus is some very special technical corpus where there are lots of 3-letter acronyms, then of course you don't want to do this, right? But so then here is just the standard. So now all we've done is define this thing called tokenizer, which is nothing but a transformer. Right? So it has some inputs and output columns. So then that's why we're calling the transform method on it. This gives us the tokenized data frame. Okay. Yeah, so for example, let's do this. We're quickly check it out. So the tokenized DF is, it has the full corpus. It has the ID from the zip with index stuff, and then it has all the tokens, right? It's kind of a pretty ugly thing. Yeah, so yeah, anyway, I just commented this because some person, because all of this is Google searchable, so just yeah, within a day the Google's bots will find it, so just be careful what you put up there. Yeah, so I'm just simply selecting just the tokens column now and just showing this. I think we were at this yesterday. Yeah, things like this, 93, this is clearly not something we want, but let's run with it for now. So now we're going to remove stop words. Okay, so there is something called stop words remover in the ML Featureizer featurization stuff. So what we did is essentially there's a list of stop words that's used by default, I think. So we simply have a link to that, and you can use get stop words to get this default set of stop words, but you can also just download it using wget and get this exact thing, put it as in the temp stop words directory, and copy that file into dbfs temp stop words if you like. Okay, so then you will have your own stop words file. We did this last time as well, right? So then you can change this. That's the whole point. So you can make your own customized list of stop words for your domain. So here's just reading it, collecting it, because I can collect because it's not too big. So I don't know. From, front, full, further, get, give, go, has that. You, yours, yourself. So then we can get into stop words length. Well, that's only 319. And now we're going to make our transformer called stop words remover. So this thing just simply removes the stop words by calling the transform method on the remover, right? And of course, we pump in the input of tokenized DFs, and so yeah, and you're setting the input and output column for this transformer. So whatever comes out is going to be the filtered tokens. Right? So whenever in doubt, just do a display or show and see what's there. So next, we're going to do a vector of token counts. So here we use count vectorizer. Right? So it will return the vocabulary size, an array of index tokens, and the array of token frequencies. So this becomes closer to the input of the KMeans algorithm. Oh, sorry, LDA algorithm. So here are two handy parameters to note: set min df and set min tf. So what are these? So this one specifies the minimum number of different documents a term must appear in to be included in the vocabulary. So this is how I'm kind of, jazzing out all those crazy strings, like these timestamp weird email strings. I know, well, I'm kind of gambling, but the idea of this notebook was to get as quickly as possible to LDA. Okay. So I can use a set min df to be a large enough number, so I will only, I can use this to make sure that I will only use terms that appear in enough documents, enough distinct documents. Set min tf specifies the minimum number of times a term has to appear in a document to be included in the vocabulary, right? That gives me some kind of term frequency cutoff and document frequency cutoff. So that's what this is. Okay, so those are standard things in NLP. So I'm defining my vectorizer as immutable, but as a new of the count vectorizer, and my set input column is the output column from the last transformer, and then my output column is now features. This becomes input column to the ML machine learning algorithm. I'm setting a vocabulary size of 10,000. So this will tell me how large, remember from last time's lecture, we have this the B simplex with all the words, the vocabulary simplex, right? That's really big now, or potentially really big now. And of course, the topics are going to be, say, 10 or 20. So we'll be doing a huge dimensionality reduction in this example. So set min df is 5. So this is the minimum number of different documents again that a term must appear in, which, maybe, just putting some numbers here, right? But there are 100 documents per topic. Have this prior information. So so hopefully, this will automatically get rid of weird email addresses and things like that, because maybe not. Right. Because if someone is very active in a news group, they'll probably have their IDs and, at least 500 documents in the same topic, then I'm screwed. But anyway, you should do proper regexing. Okay? So, so this is, so that's my vectorizer, and then I'm just calling the transform method on the vectorizer, my filter df. And I'm only selecting my ID column. Remember, from the zip with index, every document has a unique ID, and then the features, not just my count vectorized stopword filtered tokens with the minimum term frequency and minimum document frequency. Okay, that's basically the input into the input into the algorithm. I think this is where we were last time. So if you just look at what's the first element of the count vectors, it's just a SQL row object, and it has the ID and the features vector. Okay, so you can see if you take 2. So let's see. So 6139 is the vocabulary size, basically. So we did set 10,000 or something, but that's the upper bound. So, you know, not enough words met our conditions, right? Okay, so so we are effectively will be going from this 6,139 dimensional simplex, which means, you know, these are how our documents are going to be represented with these frequencies, right, in this huge high dimensional simplex. And then we're projecting that to this 20 dimensional simplex. Okay, so now I'm just converting the data frame to RDD, simply importing stuff, right? We're using a so now I just check what this thing is. So now, so here's my actual docs for LDA. So, so it has, here's the main set of parameters, number of topics. What optimizer do you want to use? Do you want to use expectation maximization, LDA optimizer, or another variant that's a faster online LDA optimizer, especially for very large data sets? This is what will work in a reasonable amount of time. What should the doc concentration be? Remember, this is the prior of the Dirichlet distribution, right? Remember, then this is very large, you have concentration, you know. So these are, you know, the alpha parameters, right? So when it's large, your Dirichlet concentrates somewhere. And if they're asymmetric, then it tells you where the prior should be concentrated. So usually we take the defaults, which will be like 1 over K or 1, 1, 1. Again, this is a topic concentration because the topics are modeled again in the multinomial where Dirichlet is the prior. And again, these are the prior parameters for the Dirichlet. Max iterations is just the number of iterations of either algorithm because they are gradient descent, they're local optimization algorithms. So that's something you want to increase. Yeah, point intervals. What else? And then you know we'll get into this concretely. You describe topics, and you can also get this topics matrix that returns a vocabulary size by K matrix, where each column corresponds to a topic. Right? So we will start pulling elements from here to make sense of output. So, okay, so yeah, online variational base. So we'll kind of quickly look at what these are. So that's just LDA, right? There's power iteration clustering, so you can do these things, you know, pretty much on your own. This is Gaussian mixture. Again, you need to know a little bit of theory, but it's not too bad. It's another way of doing non-parametric clustering, right? What else is here? K-means, we already did this. So here are the clustering methods. The streaming K-means will be streaming version of K-means. So anyway. So because we want to maybe get to Fika faster, we will do the faster version. This is the online variational Bayes. Okay, so how many of you have heard of variational Bayes? No? Okay. All right. I think that's an important. It's an important high-level idea. Okay, so let's just see what. Okay, so variational Bayesian methods. Okay, so even before I motivate variational Bayes, I have to tell you a little bit about what Monte Carlo Markov chains are and how that's your standard missionary for Bayesian inference first, right? So I told you last time that Bayesian in Bayesian inference, your primary objective is to identify this distribution called the posterior distribution, right? It sits on the parameter space, okay? So instead of a point estimate in the classical frequentist setting, where the frequentists are trying to estimate a parameter and they want a point that estimates this unknown parameter. Say the parameter is in 2 dimensions, so you're hunting a point. And what the frequentists generally do is they want to say, I have some kind of, a set I estimate to enclose this point I'm really after, such that with a very high probability, this random set, which is an estimator, will enclose the point of interest, the unknown of interest, with a very high probability. So these are called confidence intervals, right? This is classical stats 101 stuff, right? Okay, so Bayesians do a different way. So they'll say, and of course, the confidence sets are the frequentist way of dealing with uncertainty in the estimator, the point estimator, right? But Bayesians say, okay, I'm not really interested in the point estimator necessarily. I'm interested in a distribution over the parameter space itself, right? And this is what we did last time with multinomial and Dirichlet and so on, right? So in that example, the Dirichlet distribution sitting on the simplex, the parameter space is the simplex, say this triangle with theta 1, theta 2, theta 3, and you sort of encode your current knowledge about the system using this Dirichlet, right? Or how much uncertainty you have by maybe making the alphas 1/3, 1/3, 1/3, and highly diffuse. And then you have the likelihood function from the multinomial model, right? That's another contour you can visualize sitting on the same simplex. And you multiply the two and normalize it. And that's the posterior, right? Posterior density. Now, that's great theoretically, because if you have the posterior, then you are not only, and of course, as the number of sample points go to infinity, both in the frequentist setting and the Bayesian setting, you have something called asymptotic consistency. That means, the posterior will converge, concentrate around the true unknown point, assuming the model is true and all of that stuff, right? And the same way the point estimator and even the confidence set, right, in the frequentist setting will start converging. It'll get smaller and smaller and start concentrating around the true unknown parameter if the model is true. So, but this is all great, but how the hell do you produce samples from the posterior distribution? Because for Bayesian, you need the entire distribution, which may not be possible, so you may settle for just samples from the posterior, right? Because with the samples, you can find the mean of the samples, that'll give you an estimate of the mean of the density, and so on and so forth. But doing that is not straightforward, so what people have done, in fact, this is the most popular method in the, I think, last century, right? So I think this is the most used algorithm in the last century. You guys have heard of this? Okay. Okay, I've not heard of this. Okay, so this is also like a prelude to my course in the spring. So I will reverse engineer content for the future. So in a Metropolis Hastings algorithm, what you're doing is right. So before Metropolis Hastings, you should know something called the fundamental theorem of simulation. It's okay, guys, just us. Well, I think this is more important. So, okay. So what is the fundamental theorem of simulation? This is basically called rejection sampling. It's due to von Neumann, the same guy that's behind von Neumann algebras and pseudo random numbers and everything. So here the idea is very simple. You have, if you want to produce samples from a given density, all you really need is to produce samples uniformly at random, let me see, from some function that envelopes it, and then throw away the points that land below this. Didn't we do this? We did this, right? Yes, okay, I told you about this. So this is what you really want to do, right? You have some density, you don't know, maybe you don't even know the normalizing constant for the density, but you can evaluate it point-wise, right? For every x, you know what f of x is, up to some normalizing constant. Then all you need is some other function g of x that is strictly more than f of x at every x. And then all you need is to be able to sample points uniformly at random from that entire surface, right? from the x-axis to all of G. So if you have a way of sampling points uniformly at random from that whole slice of the set in 2 dimensions, then you can discard all the points that landed above F and just keep the points that landed below F and just drop them to the ground. That's perfect samples from F. This is von Neumann's idea, right? This is called the fundamental theorem of simulation. So if you can do that for any, and this works for arbitrary generality, right? It's great, but of course you can't do that, right? For posterior density, what do you want? What Bayesians want? They would want an envelope function sitting on the posterior density, say on the simplex, and then be able to produce points uniformly at random from the envelope above the posterior, right? This is not easy to do. So the alternative is a local method. So this is where Metropolis Hastings comes in. So this is actually from chemical physics in the 50s, right? So the basic idea is you're trying to sample from P. This is your unknown, right? Say the posterior. And of course, you only know how to evaluate it point-wise, right? This could be in any dimension. Suppose you're here, then what you have is something called Q of X, given where you are. So this is called the proposal density. So it could be a Gaussian with some, say 1/10 as the variance at the current location. And then you can produce a point uniformly at random from this Gaussian centered at the current location. That's called your proposal, right? So now you propose a point. Now the question is, should I accept this proposed point or not, right? That's where the Metropolis Hastings idea comes from. So it's called a accept reject step. So all you do is basically look at the ratio of the value of P. I think this is basically it. Yeah, so you basically, for each iteration, you generate a candidate X for the next sample by picking it from the proposal. Well, it's called G instead of Q. Okay, then you calculate this thing called the acceptance ratio, which is alpha. What is the acceptance ratio? It's the unknown density F evaluated at X, the proposed point, divided by the density F evaluated at the current point. Okay, so it's this ratio. Of course, this ratio will be more than 1, right? If F is bigger at X than at XT, it'll be greater than 1. Okay, so that's basically alpha, and then you have to decide whether to accept this proposed point or not. So then the way you do this is you generate another uniform random number, U, okay, from the interval 0, 1. If U is less than or equal to alpha, then you accept the candidate and set the next iterate to the proposed candidate. If U is more than alpha, you reject it. Okay, so that's basically the idea. There are a few things missing here. There should be maybe a minimum of alpha and 1 or something like this. Okay, it's fine. The definition is fine. So if alpha is more than 1, you will accept all the time. Okay, right? So you see, if f is bigger, if f of x is bigger than f of x sub t, you will with probability 1 go there, right? There are a little few corrections here. You need to divide by the proposal density and things like this, but anyway. So what's your question, Mariam?
No, I was thinking, I think we use the same method for simulation of simulations.
Yes.
We have this Monte Carlo metropolis criteria where we have this Boltzmann distribution.
Yeah.
So then you generate energies, and then if the energy is like greater than another energy, you count.
Yeah, right. That's right. So it sounds like it. So this is also called Gibbs sampling somewhere. Yeah. So anyway, I mean, you guys can figure this out. It's not too hard. It's very intuitive, right? So you will always go to places with higher density. If your proposal is symmetric, you'll always go to places with higher density, right? And if you're proposing to go to, say, x prime, and f at x prime is less than f at where you are, right? You will still go there with probability proportional to how low it is. So it's kind of a drunken walk, right? Still kind of going always uphill, but like it also goes downhill with some probability. It's kind of some intuition. The nice thing is this if you just do this for a long time, then the sample, this is a Markov chain, right? So it's because your entire history of all the places you've been to doesn't matter. What matters is only where you are. So that has this Markov property. So if you kind of jump around like this and look at the trajectory, that will converge to a sample from the true f that you're after. If you let time run to infinite, right? So you can kind of use time to basically produce samples by only evaluating the unknown f at any pair of points. Okay. Is it clearly? It's too fast. Well, anyway, I'm kind of like, okay, this is normally like a full lecture, right? Okay, what's variational base? So this is just primer, right? So of course people do MCMC, and Gibbs sampling is another word for the same thing basically, and physicists also call it Glauber dynamics. Doesn't matter. So these local methods are great, but they run into problems quite quickly. The main problem is when the data is large, it's not easy to evaluate this. This becomes computationally quite expensive. Okay. Well, because you have to evaluate the likelihood at all the points, and if all the points are just millions and millions of points, how do you do it, right? So that's and also the other main problem with MCMC, Monte Carlo Markov chain is what it's called. It includes Metropolis Hastings and other generalizations. The problem is you never really know, except in special cases, if you've truly converged, right? How long do I need to run the chain to make sure that I'm at stationarity? That's not a trivial problem, okay? To do it exactly, it gets quite complicated. You need to really get into the structure of the particular problem. And so people do various heuristics, which works most of the time, right? I mean, gradient descent is heuristic anyway. So, so variational Bayes is essentially another way to get the posterior without doing MCMC. So it essentially turns the posterior sampling problem into an optimization problem. Okay, this is a very high level what variational Bayes does. Okay. Yeah, it's a family of techniques for approximating intractable integrals arising in Bayesian inference and machine learning. They're typically used in complex statistical models consisting of observed variables, as well as unknown parameters and latent variables with various sorts of relationships. Okay. So the standard way to attack this would be, how do you, so in general, you come up with some kind of a mixture approximation for the posterior. So the posterior will be a very complicated thing, right? It's the product of the likelihood and the prior. So instead of directly going at that, you may actually approximate the posterior using, some rich enough but easily implementable family. For example, you may use a mixture of Gaussians to approximate the posterior, and then hunt the parameters of this mixture, right? So it's okay. All right. Let's not jump too much into it. We can come back into this if we really want to. I want to.
Mix the different distributions.
Yeah. So yeah, that's the standard approach. Would be to use a parametric form that's not too complex to approximate the posterior, and then turn that posterior sampling problem into an optimization problem where you're estimating the parameters of this, what they call SemiParametric model, right? Because with a mixture of enough Gaussians, you can approximate any density, for example, right? There's a little bit more going on, right? So people's whole careers are on variational Bayes. So, but let's watch maybe, because I kind of want you guys to do stuff as well. So let's fix the number of topics to 20. I mean, this is kind of cheating because we know there are 20 news groups, but let's do that for a minute. And what I'm now doing is, bringing in the LDA and online LDA optimizer. This is the one that implements, a batch mode optimization method. So it has this parameter called set mini batch fraction. So I'm actually setting it to be quite high here because the data set isn't too big. Then I'm setting the number of topics to be 20 from before. Max iteration is just 3. And I'm setting the document count. So -1 uses the default values. I believe the default values are 1/111 and maybe 1/k for topic concentration. So you can figure out what the default values are. Downstairs as an exercise how to do it. So here I'm just, you know, I want to convert the ML vectors into MLlib vectors because we're using this RDA-based library for machine learning, MLlib, the older library or the original one. So it's just some little conversions, and then I need an RDD, so I do a .rdd, and now I've run the LDA model that I've set up with this. So let's watch this, and then have Fika. Come back. That's terrible.
All right, thanks for that introduction, and my apologies.
This is the same day.
So I'm going to be talking about a new fast learning method for fitting topics in the topic model latent density allocation. So latent density allocation, or LDA, is a hierarchical Bayesian topic model. It's a model of document collections, and the way it explains the variation in a set of documents is in terms of the set of latent topic distributions, which are basically just distributions over the vocabulary in the corpus. So in these topics, what you tend to see is that words that have something to do with one another tend to have high probabilities. So for example, a topic about business might give high probability to words like corporation, money, million, dollar, etc. So what we'd like to do is fit these topics efficiently to very large data sets. The way that is done is using posterior inference, but unfortunately the true posterior, as it so often is intractable to compute exactly. So we have to appeal to approximate inference methods. The one I'll be talking about is variational Bayes, which is a deterministic alternative to the more commonly used Markov chain Monte Carlo methods. The basic idea is that instead of trying to sample from the posterior distribution, we're trying to optimize some other distribution that has a convenient form to be as close as possible to the true posterior we're interested in terms of KL divergence. And the nice thing about these methods is they tend to be fast compared to MCMC methods. They tend to converge in fewer iterations. But they're still batch methods, and so they scale linearly with the number of documents, and therefore can be slow for very large data sets. What we'd like to do is to be able to fit these approximate posteriors to our topics without having to look at the entire corpus every iteration. And the way we do that is using a variant on the stochastic gradient method. So it turns out that you can actually derive a I won't go into the details, but we can talk about it in the poster, but it turns out that you can actually derive a very simple stochastic natural gradient algorithm for optimizing the variational objective function that only has to look at one document or a few documents at a time. What this graph is showing is basically the progress that this online algorithm makes compared with the corresponding batch algorithm. The y-axis is perplexity. It's a measure of model fit, lower is better. So this red line is the progress made by the batch algorithm fit to just 3% of the corpus, and it's slow by comparison to our online method, very slow. Basically this is just a very, very fast way of fitting topics in LDA to very large data sets. The nice thing about this method is that it's actually applicable more generally, not just to LDA. There's nothing special about LDA, so we look forward to applying it to other models. And also just want to mention we've got implementations. I've got some Python code on my website. Now it's been incorporated into the Scalable framework as well. And that's a very fast implementation. So please come to the poster. It's W80 in the probabilistic model section. Thanks.
Okay, so that's a lightning talk and some nips. I like these talks, right? So he's the guy, right? So he's the same guy we watched the video of, right? But this is how long ago is this? 2010, 7 years. So this single-handedly made the machine learning research citations go off the roof, right? So it's pretty, yeah. So, the objective function he's talking about is called KL divergence, right? So KL stands for Kullback-Leibler. It's a metric on the space of measures, right? It's a distance on distributions. So anyway, you can look up what it is, but let's sort of, I'm kind of giving you enough teaser so you can like go and quench yourself to whatever depth you want, but we kind of will try to keep things a bit practical here and start jumping into analyzing this data more now. Okay, maybe after a cut. Yeah, I also have this. I don't know, alternating these squares. This is the other main thing in data science recommender systems. So I thought I'll do this in the second half, but I'll save it for maybe later.